not just have these three choices for A, B, or C. If we don't investment in A, B, or C, we can put the money into the money market, and put into the money market. We have 5% of interest for the next period. Okay, so time or period we can treat it as a year or months. 1 year, 0 year, the year 0, year 1, year 2, year 3. So different investment or putting different choices. We have different percentage in return. Okay. So our objective function is that we try to maximize total cash in the end of time 3. Okay. Okay. So let's talk about the variables. We have xi in A, B, or C, right? So that way it will be XA, XB, and XC. You can say in investment I, and I is equals to A, B, or C. And if we don't put it into investment A, B, or C, we can put it into the money market. We utilize an N. Indicates that. And for different, because for each period or for each time, we do have a choice to put into that. So in each period, you can determine how much money I can invest in money market. So NP indicates the money. So the T. Zero, 1, 2, 3. Are you sure? At time 3, I want all my money back. Should I put my money into money market? So the T only 0, 1, and 2. Okay. So our objective function is that we try to maximize the total money I have at time 3. Right? Okay, but that's the consequence. The money at time 3 actually is the consequence from time 0, time 1, and time 2. And time 1 will influence the result of time 2. Also influence the time 2, and come back to influence the money we have in time 3. Okay, so that's why even we want to maximize that, we start from time 0 see what happened. And for time 0, time 1, time 2 becomes our constraints. Because this relation will influence the result of time 3. Okay? So let's talk about time 0, what happened. Time 0. At time 0. At time 0 we have 10,000, right? We put into two separate parts. We have some equality. The left hand side, well, we talk about the money we have. The right hand side talk about investment we want to determine. Okay, so in time 0, the money we have is 10,000. And right hand side, our choice will be XA, XC, and M0. Okay, because what do you think about that? Because you can see investment B we have 1.9 at the end of time 3. So we'll probably keep some money for the period 1 investment in B. But simply we just hold this money. It's not good enough. So we put this money into money market to earn something. Okay? And once we get the money market, or once we put it into the money market, for the next period, time 1, we will have how many return? How much money return? M0. And that's the point 2. 0.2. Let's talk about it first. You say point 2 XA. That's because I put $1. At time 0, I will get $0.2 back at time 1. Okay? But we don't have for C. So what else? M0. We put in the money market, we can have some interest back. 5? Are you sure? 1.05, that's 5%, right? Okay, that's the total money we have in time 1. And for time 1, our investment could be XB and M1, right? So how about time 2? One 1.5 XA and 1.5 XC and M1 equals to M2. Because right now we don't have any investment available, but we still have a choice to put into the money market M2. That's for time 2. So the result of time 2, period 2, will influence the time 3, the money we have. So actually, the objective function is the left-hand side of the time 3, because at that time we don't have don't have any investment. We only have the money we have. Okay, so our objective function is (1.9) x xb plus and
1.05 and 2.
okay,
7,000.
7,000 for okay. Okay. Questions?
Non-negative.
Mm. Okay. This example just try to tell you that unlike the previous ones, we can define the objective function in the very beginning. But for this one, I didn't define it in the very beginning. I define the constraints first, and based on the relation, I go back to find the result of the objective function. Okay? So you can see this example just a different option. When you try to write down the formulation, not always, sometimes we cannot write down objective function immediately because the objective function sometimes are the result of the constraints. Okay, sometimes we do that. Okay. So any questions? Before we continue, homework. Two weeks from now. Different sections, they have their own problems. Okay? Some they looks a lot of them. You probably, when you have a lot of problems, you will find that they are pretty easy. But maybe only one of them is need some time to think about it. In the future, probably you will have few problems. If you find few problems, actually they are very tough. Okay, it will take you some time to think about it. Okay, questions? I think for this one, it's only for formulations. Okay. Okay, we continue to talk about another example. Formulation. Okay, the example actually is sometimes you will see that we try to determine the location of the facility. Okay, so for example, in the very beginning we have two facilities, shipping and steel manufacturing. That's a coordinate. Okay, that's a coordinate. And right now we have two new facilities. We'll be adding to this plant. We'll be testing and assembly. So if I want to minimize the trips, it means you can well guess that the testing and assembly should be around here. Should not be outside of. Okay? Should not be here, should not be here, should be located here. But we still want to determine what should be the location of the facility. Okay? And assume the trip, for example, from the steel to shipping, the trip's only north south, north to south, south to north. It's the rectilinear movement. Okay? So it means that for steel to shipping, we'll move from here to here first, and then move from here to here. So the distance will becomes this one plus this one. Okay, write that. From steel manufacturing to shipping. It based on different, based on our definition. Sometimes they utilize Euclidean distance. So if that's a Euclidean distance, that's for you for me. That's the green line. Okay. But in our example, that will be a very nice. The calculation of the distance based on that. And also most of, because the row just looks like that's the mini one. So sometimes in the row we try to calculate the distance. We utilize the rectilinear distance to represent it. Okay? So how will be our variable?
X1 to 4.
X1, what?
X1 and X2.
X1 and X2. What does the X1 and X2 indicate?
The coordinate of the steel and casting.
We have two facilities. So we want to determine the coordinate. So for casting will be C1, C2. For example, casting in location in X in horizontal, C2 is the vertical, in X-axis and in Y-axis. So that's the location. So for the assembly, we will A1 and A2 indicates the location of assembly. Okay. Okay. So what is our objective function?
Minimize.
Minimize. Minimize the cost of goods. number of trips means I have to move for 40 times. And that's the distance. So I need the distance between them. We have a larger distance, we have more cost. And it looks a little bit like waiting because we have moved so many times. So once you can say the casting assembling, we have moved so many times, you can expect that these two should be near to each other, right? To decrease the cost. How can I calculate? Maybe we can calculate the distance first and transform the distance to cost. Because the distance, that's why I say from here to here, I need to calculate the in the red distance. Think about this idea. Suppose this is x1, y1, and this is x2, y2. How can I calculate the distance?
X2 minus X1 for absolute value. Plus Y1 minus Y2 minus Y1.
So we don't have any idea of which one is larger than which one, so we put the absolute value of that. Okay? So since we have 4 different types of trips, so we calculate for 4 different types of trips. So for the first one, will be casting to assembly will be C1 minus A1 plus C2 minus A2.
And divided by 10.
That's the total distance, right? Okay, suppose that's in feet. I didn't write down the unit. Suppose that's in feet. So it should be divided by
100.
100.
divide by 100, right? Divide by 100.
And multiply by 10.
Multiply by 10. And also,
40.
and 40 times. Okay? 40 times. Okay? That's the first one. How about the second one? Steel to casting. C1
C1 minus 900.
C1 minus 700. C2 minus and
And 10, 80.
$10 and 8 times. Okay? And we have more. That would be steel to assembly. Steel to assembly. That's an assembly, location of assembly, location of steel manufacturing. And then the final one is shipping and assembly. Shipping Or can I calculate it? A1 minus
A2.
A2, right? Okay. That's our objective function. We want to minimize. Number of the cost of trip between facilities. Okay. Do we have any constraints?
Professor, can it be in one place for the casting or the assembly? For example, in the same place like the steel manufacturing?
Assembling and casting will lay in the same press. Maybe or maybe not, because you can say that if these two, to steel and shipping, if assembling to ship and steel and shipping is the same as the casting to assembling and steeling and steel manufacturing and shipping, if they are exactly the same, so then the assembling and the casting will be the same place. But right now, they don't have exactly the same trips from, for example, assembling to steel and to shipping. The casting to assembling to steel maybe I write it down. Let's assembling to the other press. But here, let's casting to steel. We don't have casting to shipping. Okay? So they are not proportional from casting to the other facility or assembling to the other facility. If casting to the other facility exactly the same number of trips and number of costs as the assembling to the other facility, then casting and assembling will be in the same location. But right now, they are not exactly the same. So in my wild guess, they are probably not. From this one, you will probably say they should be in the same place. But for me, I would say they will be very close to each other because we have a lot of trips. I would say they will be very close to each other. But if they are really should be in the same place, it depends on the green and the red part if they are exactly the same or not. If the green and the red part exactly the same number of trips and same number of costs, then casting and assembling will be in the same place. But right now, I cannot say that. But my question is, you didn't answer my questions. Do we have any constraints?
The
Negative.
can be
Negative. Do we need that?
No, because
It could be in any place, right?
so no.
No? So we don't have any constraint. Are you sure? When you learn linear programming problem, it's not possible you don't have any constraints. If you don't have any constraints, the linear programming will become next week.
Unbound.
Unbounded will become unbounded. But Is possible unbounded?
Maybe C is lower than 100.
C1 is
C1 is lower than 100.
that's what we expect. Probably this should be
In the area.
this should be I guess, from my guess, this should be in this area. This should not be outside of the triangle. Because we want to minimize the, this should be located into this triangle. But we still don't need this type of constraint. Because when we try to minimize them, it will give me a solution. I still don't have to write down the constraint. As what we learned about programming problem, we prefer the constraint as less as possible, right? When we have a lot of constraint, we are in trouble. So do we have any constraints? Currently, we don't have. So my argument is that when you learn linear programming problem and you find that there is no constraints, they are unbounded, right? So is that unbounded? It's not unbounded, so my argument is not correct. Okay? My argument is that if there's a linear programming problem and I don't have any constraints, it will be unbounded. But let's check. It's not unbounded. So what does that mean? And we don't have any constraints.
Boundary is using the objective function.
In object, as what we say, we can expect that the location should be in this triangle, but we don't need that. Because when we try to minimize it, we can find the location, C1, C2, and A1, A2. I can find it without the constraints, without these constraints. Not maybe. This is non-linear programming problem. Why?
Because absolute value.
Because absolute value. It's non-linear. Okay. So
What's the difference between the absolute value and the normal?
okay, let's check about it. Suppose as f of x as x. Suppose f of x is equals to ax. That's what it looks like. Right. A straight line is a linear, right? See, it looks like this. But f of x is equals to that's it looks like.
But in a problem that's all of the variables are not non-negative. So I think that's the positive region is similar.
But here we don't have non-negative assumption, right? Here it could be in any place. So the entire domain is non-linear. Okay? So the absolute value give us trouble. So write the following topic. So when we have absolute value in our objective function, they are not linear programming problem. Like this example. It looks linear, but we have absolute value in our objective function, so it's not linear. So if I want to utilize a simplex method to solve this kind of problem, it means that I have to transform this absolute value into the other form. Okay, so that's why when some of you, PhD students, you're already working on your research, you'll find that some, for example, distance, actually it's not linear. So how can you utilize different or maybe adding more variables? Try to transform them into a linear one. Okay, for example, that's a piecewise linear formulation, piecewise linear function. If I check the entire domain from here to here, this one is a linear programming problem. But if I separately to discuss this problem, say for this domain I only discuss this function, that will be linear. And if from this segment to from here to here, I only talk about here, that would be linear. Okay, so that's why you see that that's a piecewise linear function. Okay, maybe simply you will say, okay, I will just solve them by non-linear programming problem. But in the end of the semester, you will find that to solve it as a non-linear programming problem is not an easy one. We try to solve them as a linear programming problem because linear programming. So that's why we put a lot of time in linear programming problem. Because linear programming problem, we have a lot of property and will give me a very good result. Can find the optimum solutions. So that's why we take a lot of time in linear programming problem. Okay? So the question is that that's non-linear programming problem. So I want to transform it. So but we still have absolute value. But we add one more variable, x3, and x3 to represent that. So right now, we only have focus on this absolute value. How can I transform them? Okay? The following discussion is that we can write down change x3 to x3 prime minus x3 double prime. And we let x3 prime greater than equals to 0, x3 double prime greater than equals to 0. And also, okay, example. If x3 is it sorry, x3. That would be
3 0.
3 0. Only, right? 3 0 only. Because I need x3 multiplied, x3 prime multiplied by x3 double prime equals to 0. If that's minus 5,
0 5.
that would be 0 5. Okay. So that's an example. So how can I represent the absolute value of x3? So it means that I try to find out this relation and this relation. The absolute value of x3 is equals to right. It looks simple, it looks easy, but it's not easy. Okay? That's why I say the formulation actually is the hardest part. Okay? So we already know this one is still not non-linear programming problem. So based on this relation, we can change this formulation as minimize. X3 prime plus X3 double prime. And our constraint is, again, we change the X3, the absolute value of X3 and X3 to X3 prime and X3 double prime. So X3 is replaced by this one. So after the transformation, it becomes linear programming problem. Okay. Questions? No.
We have the x3 x1 and x3 2 multiplied times 0. So it's okay.
Good questions. I didn't add this one to express. Why? I didn't write it.
Still non-linear. Or
If I add this one, it's still nonlinear. But I said, but I don't need that because if I don't have this, if I don't have this constraint, it could be 7, 4, right? So, but the objective function will provide you 3, 0 or 7, 4. If my solution is x3 equals to 3, suppose, and without writing these constraints, the objective function value should be here or should be here. Should be the blue one or should be
Oh,
the blue
blue
one.
because the is minimized.
Because I say x3, I want to minimize x3 prime plus x3 double prime. So I will choose the smallest one. I will not choose this one. Okay? So the reason I don't have to write down this, because it's objective function. Okay? But sometimes, if there's a maximization, problem, you need that. So it means that we are in trouble. We have to transform them again. Okay? So any other questions? No questions. I forgot to mention that. Probably I will change the classroom back to management building, but I'm not sure because we don't have enough information because the deadline of the dropping day is result day is next Monday, right? And after that, I have to make I can make sure can I move or not, but I'm not sure. So next Wednesday before you come to class, check Moodle. If I can change the classroom, I will announce on the Moodle. So if you see nothing on the Moodle, so it means that we're still here. Okay? So if you see something on Moodle, you have to move to a new class. Okay? Any questions? I see you next week.